Hello, and welcome to the Artificial Intelligence in the Energy Industry webinar. Our webinar today is with Navigant Consulting in partnership with InfoCast Events. Today I have with me Sean Chandler, a Director of Grid Modernization at Navigant Consulting. Sean, if you have any questions during the webinar, please let me know and I'll keep advancing these slides for you. If the audience has any questions, please remember to type your questions in the Q&A box in the lower right-hand corner of your screen. We will answer your questions as time permits. Thank you so much, and now I'd like to turn it over to Sean Chandler. Welcome.
Good afternoon, everybody. I'm Sean Chandler. Thanks again for the introduction. I'm glad folks were able to be with us on the call today. Today we're going to be talking about artificial intelligence in the energy sector. The agenda today, I'll briefly introduce AI. We'll talk a little bit about a few types of AI and some of their features. We'll dig into some application areas and adoption of AI in the industry, and then we'll talk about specific value drivers and some expectations for the future. Let's go ahead and go to the next slide and jump right in. So we really can't talk about artificial intelligence unless we start with complex systems. Complex systems and artificial intelligence, they really go together hand in hand. The idea of a complex system, we have to think about a large number of features and interacting components in a system first. That's common in social systems, it's common in energy systems, and it's certainly common in biological systems. These all, when you think of the way that you pass information from person to person, or how communication and information assists us in the energy industry to move large amounts of information, and in a body, when you think about different parts of a body being connected and all having different components and features and characteristics, when they all blend together, the understanding, we have an aggregate activity which is nonlinear. It's very difficult to predict the activity of any of the individual elements in the system just from their activity alone. Let's go ahead and move on to the next slide, please. So when we think of artificial intelligence, now in respect to complex systems, we have to think about it in specifically if it's strong AI or narrow AI. These are words that are used to describe machines with the ability to apply their intelligence to a problem. When we look back through time in terms of artificial intelligence, most of the efforts, most of the characteristics of AI that people are familiar with, you'll think of thinking of strong AI, where, well, we have a machine and gosh, this can solve any problem. But here today, we'll be talking more about narrow AI, which is where we take a machine and we give it the ability to apply its intelligence to just a very specific problem or a very detailed task. And with that, then, it's the application of machine learning for the purposes of automation and computational supported decision-making. And here, because it's in a complex system, we're taking large amounts of data, very large amounts of data from very many different sources. We're drawing all that together and allowing a machine to help make a decision or support the decision of a human operator, which is oftentimes how it's applied within our own sector. Let's go to the next slide. So in terms of the applications of AI, looking back through time, it's 700 years for automatons, which have been developed, and 400 years for calculators. Most people think of AI as being only applied in the last 50 years, but if you dig into the system science of it, then artificial intelligence is really based on syllogistic reasoning and logic, which goes all the way back to the 4th century BC. So we can talk about the tough problems. You know, what's really hard in our industry? Where can we find the most value? And we can say that that's in classification problems and optimization domains. And we'll talk a little bit more about that in just a few moments. Let's jump to the next slide. So thinking of types of artificial intelligence, we're now digging down into the domain itself. And well, what kinds of AI are there? We talk a lot about learning machines, but what kinds of programming make these machines, give them access to what we would call learning? So the first type of AI, just briefly talk about this artificial neural networks. Now, these are the most common. They're inspired by the body and neuron a neuron itself with an axon and a dendrite. These kinds of systems, they can be trained and they can learn. Key characteristics that they're very fast and they're also very common. Generally, this is most often used in our industry and in other industries. When we think of AI, we're calling out on artificial neural networks. A second kind of AI is a particle swarm optimization. Now, PSO, these are inspired by the flocking behavior of birds. You can think that the movement, you trace the movement of birds through the sky. How do they do that? They have very simple rules that they follow. If anyone on the call has seen a flock of birds, and it's almost elegant, the way that they fly together, and the idea that they're all communicating together, that's a falsehood. Birds don't tell each other how to flock. They simply move together as one. A bird tracks its nearest neighbor, and as that bird moves, they try to keep the distance between them, or at least we suspect that distance mechanism allows the flock to form. Well, by using this kind of behavior, we can do very fast searches of very large solution sets to find optimal solutions. And here, this example I've shown you is an unusual surface with maxima in many opportunities to optimize across that surface that you see. And particle swarm optimization would be particularly effective at searching into these spaces because the method that it functions, each of the birds, call them, the algorithm itself, the components in the particles, the algorithm itself is following mathematically the most optimal neighbor. So if a neighbor discovers a path towards optimality, then the other particles will turn and follow to explore that section of space inside of a solution set. Particle swarm optimization is very, very good at finding optimal solutions inside of very, very large solution sets. So then there's agent-based simulations. Agent-based simulation is inspired by real systems, generally human beings, and the rules and the behavior that we have as individuals when we talk to each other, we communicate with each other. So an agent can have a set of simple rules, and if a rule, a profile for a decision is allowed by a particular algorithm, these computer programs called agents, then they can search for solutions. The computer program can search through a very large set. What's very interesting about agent-based simulation is that the agents themselves, even working in simple rules, can reproduce extremely complex behavior. Now, agent-based simulations are not quite as fast and certainly slower than particle swarm optimization or artificial neural networks, but they can be very good for reproducing complex behavior. There are very good examples of agent-based simulators out that have been used in social research and social science and simulating crowd behavior, for example, or forest fire behavior is another good example. These kinds of tools are excellent for planning behavior of large populations with slightly different demographics or even communication systems. I myself have used agent-based simulations to reproduce a variety of industry phenomena in the uptake of technology and, for example, the impact of weather on a solar farm. Let's go ahead and jump to the next slide. Another type of AI people would be familiar with, at least in name, is fuzzy logic. Fuzzy logic's been around for at least 40 years. And here we're talking about training a system to define a solution to a problem where there's gray areas. So we relax boundaries of decision criteria. Here I've shown you an example where we're looking at something that's hot and something that's cold and something that's warm. Well, what makes something cold and what makes something warm? So the idea is that if we have a machine that can watch some function and we give it a set of training from experts and say that under these criteria you decide A, and under some other set of criteria we decide B. And if it's a mix of criteria A and B, now we can relax the boundaries and identify other criteria that may add to the decision to inform it. This is commonly used in control theory. Fuzzy logic has been used a very long time, and so this is good where we have discrete decisions. So if something is found with some criteria, then yes, we absolutely need to do this. Fuzzy logic is excellent, and most people will be familiar with fuzzy logic in application within networks of resources in the SCADA system. So, for example, if some condition is met, then do this. Ladder logic is a form, but again, it's a harder decision-making, discrete decision-making, because you can say if some exact criteria is met, where fuzzy logic, you would be able to relax some decision criteria and then inform decisions because there's some grayness involved, let's say between two or even more criteria. And then finally, genetic algorithms. Now, genetic algorithms are inspired by genetics, as the name suggests. They're also called evolutionary algorithms. Genetic algorithms are a class of evolutionary search mechanism. And here we look at a population, and this is in this example that I've shown the graphic. We have a population, and each of consider a gene as a solution. So blue might mean some information, black means another piece of information, light blue means yet another piece of information. Here in this set, our population is composed of members that have 6 genes each. And you can see that they're randomly distributed, the answers, so to speak. And we take that population and then we evaluate it. That's called a fitness function. How well does this particular genetic answer, again, it's a combination of variables. You might think of, let's say, a portfolio management solution for a power marketing floor could use genetic algorithms to try to find the best combination of hedges in order to guard against risk. And there's some fitness function that we'll use to apply to the population to determine what are the best combinations of portfolio options that we have in order to come up with selection. Now that selection is important here because once the fitness function has been performed, now we select a number of that population and we terminate the remainder of that population. What's interesting in genetic algorithms is that over time, many hundreds of thousands or even millions of populations of solutions can be tested and mutated and crossed over with each other to search a very large solution set to search for optimality. Genetic algorithms are slower in their effectiveness because, again, you're doing a very broad search. You're using the value of randomness to look deep across a solution set rather than some brute force methods where you're just trying to solve for everything and find the most optimal set. But they're very good for finding optimality in large solution sets, but just a little bit slower. So they're good for planning. Let's jump to the next slide. Now, there are other types of AI, absolutely, and these 5 that we've talked about here very briefly are common, and you'll find them in the technical literature. What's key is the application of AI into what we would call leverage points. Now, I'm saying a leverage point because that's a call out to a very specific approach from a system scientist that I'd like to call to your attention named Donella Meadows. Could write that down, who talks about the highest and best leverage points in any system. We start to think about general systems, meaning any system that exists. When you think of the highest value, what are the highest value leverage points in our own industry for artificial intelligence? How can we move forward our industry quickly, and where should we be looking? Well, we've identified in a paper from Navigant what we call the energy cloud. And many of you are familiar with the energy cloud, and at least in concept, because it's this idea that we're moving from just tens of power plants to millions of power plants very, very quickly with distributed energy resources. The network orchestration and the splitting of our industry into separating it out into different functions and different characteristics that are managed by different entities within the value chain, whether it's a distribution value chain or a logistics. The idea here is that communications and security, big data, and then the prediction of events in the future, and then system operations, we'll be thinking of these three areas as high value leverage points in the system. If we can use AI to help us with communications and security, that will help our industry move forward quickly. AI helping us with analytics, predicting the future, utilizing big data, and then applying all this AI into system operations to help make better decisions quickly. So let's jump into some of the examples. Let's go to the next slide, please. So the real challenge is to take computational intelligence or artificial intelligence and think of it over time. How do we first break down these forms of AI and think about all the features of our systems? Well, in energy, and I come from the electricity side of the energy industry. Of course, we have oil and gas and water and natural gas. The distribution of energy comes in many forms, but today we'll be concentrating on electricity. When we think of electricity, and we have reliability in operations, there's sub-seconds to days. We need to very quickly make decisions in operations, and we need to very, very quickly make decisions for reliability purposes. And so that's typically why we use a machine to make a decision without human intervention. We get down into the 4 millisecond range for system protection functions, and in the days in order to guide operations in preparation for storm or in response to outage. So how we manage those operations, we tend to need tools that are very fast. So there's one applicability area here that's very fast. And then in the middle, the management of distributed energy resources and their planning, electricity service providers and customer systems. Generally, we have a few minutes to optimize in these systems up to many months ahead of time. On the customer side, customers would love to know how you're going to utilize their distributed energy resources a month in advance, if you could, and then even minutes in advance or days in advance or weeks in advance. Many distributed energy resources that we're all familiar with on the demand response side, given, if we look all the way back to Amory-Lovins in the 1970s and demand side management, we start to think about how we've been managing these systems for the last 40 years. Well, none of that's changed. Behavior, the human behavior side, human beings would love to have advance notice. So we have a need there for AI that can operate fairly fast, but for optimization, if we really want to dig in to do deep optimization, try to find the absolute best solution, that we may even have as long as a month. And then we look towards the planning horizon, another area in our industry where we could separate out. We have minutes for some plans, and we're thinking about outage, to many, many years if you think out far in advance for generation planning or integrated resource planning and the like on the regulatory side. So the key here is that coordination across time is the key to success for all control and system optimization. So how do we draw all these systems together into one long horizon, from very short to very long, and how do we apply these AI tools? What we're talking about here is platform systems of systems, where a system can draw upon some types of AI for very fast decision making and other types of AI for other decision making. And can we draw all that together inside the same big data platform in order to get to the decisions that we need, and at the same time changing the services and the tools that we use despite the need to access the same data? Let's jump to the next slide, please. So here we have a classification of artificial intelligence opportunities at a high level, and there are many different opportunities in our sector, and this is certainly not all of them. I've tried to follow our line of reasoning from earlier in the call, that we have classification and optimization types of problems, optimization here in green and classification and prediction in blue. And let's just start at the top, and we'll move quickly through these. All of you I'm sure we'll have examples of your own. In distribution, some interesting and very recent advances in AI for doing phase identification and meter to transformer mapping. Also in distribution, determining weather, and weather also applies down in distributed supply and generation portfolio. When we think of solar, certainly total sky imaging. There's been a couple good grant projects that have come out. Let's see, ARPA-E had a great project called Nodes, looking at distributed intelligence, and then Sunshot, also another good grant program in North America, which was looking at the classification of solar profiles for prediction of weather in advance for cloud cover in large solar farms. Those are all good examples. Another good example in distribution in fault analytics, high impedance fault identification and outage identification and prediction ahead of time, alarm classification and situational awareness for distribution and transmission operations, all key for utilizing a operator-based approach rather than a technology-centric approach to situational awareness. And let's just say something very quickly about that. When you're designing your system operations around your operators, the operators have certain cues and colors and screens which are common to their management of events and their management of situations in real time. A technology-centric view means that you're training an operator to use a specific piece of software. And as you grow the need over time to have additional capabilities, you, instead of changing the platform in a human-centric view, you just add more software. The problem with adding additional tools, and in this case, new colors, let's say for an alarm, or a different sound for a different type of alarm, when we do that, we start to complicate the system inside the human mind and actually make it more difficult to make fast decisions certainly in very fast operations requirement areas such as distribution ops and transmission ops and power marketing, power trading in minute level markets, or even 15-minute markets, or even hourly markets. It's important to have cues which are consistent over time and using screens that are consistent for situational awareness with the need for quick situational awareness. Another area inside distribution is reliability-centered maintenance, understanding how equipment changes over time. It's typically called the bathtub curve. What's the probability that something will fail? And how can we predict that failure over time? That's a classification and prediction problem. We'll jump forward into customer service, assessing theft, and I'll move through these quickly. Growth patterns and call routing and IVR systems, all excellent examples for how we can use AI better in customer service. For example, if you're expecting an outage in a certain location and a customer and calls start to flow in, then it's possible to route based on that advanced information in some cases, and the like. In generation, again, RCM maintenance, very important for plants, reliability-centric maintenance, plant and asset health management, understanding the asset health inside of a plant. I don't know any plant managers in my career that welcome forced outage. You just don't find that. So in generation, the ability to expect a fault in a part through vibration analysis or some other baseline analysis of a part or a process's behavior is key and critical to effective modern plant management. Also in generation, on distributed supply and generation portfolio management, understanding and predicting weather and how weather impacts, let's say, run of the river for hydro plants, or how supply, the coal pile affects a coal power plant, or in distributed systems, how the distributed energy resource supply matches with your generation portfolio, and how to best optimize the use of these new millions of resources. We'll talk about that more in a few minutes. On the regulatory side, we're jumping into the planning area, and then also some very fast response classifications around critical infrastructure protection and threat identification and response. capacity-driven rate design, load and revenue forecasting. A lot of great work in load forecasting in AI, specifically particle swarm optimization, agent-based systems. Agent-based simulation is excellent for load forecasting, and as well as it's commonly utilized with artificial neural networks used for load and revenue forecasting and program design, effective program design. Jumping over onto the optimization side, we have operations and markets and products and services that I've called out as specific areas of interest, and certainly on operations, everything we'll talk about here in a few moments with distributed energy resources. You can see we've got home energy management systems, solar, microgrid, storage, electric vehicles, mobile storage. The idea that we have many in the future, even with autonomous vehicles, how many vehicles do we really need in order to get an effective base response that we can have as a hedge against some balanced portfolio approach for in supply, some power plant. How many of these roaming resources do we really need? Is it 1,000? Is it 100? And we can use AI to explore that question and try to dial in on the least amount that we need at any one time, or the maximum amount that we would prefer in order to elicit a specific response in the system. Truly, the need for AI is strongest, in my opinion, with distributed energy resources. We'll talk about that a little bit more. Also in asset management and controls and assigning maintenance, and TSP refers to something called the traveling salesman problem. How can we move through a service territory with one truck and most effectively get to all the points of interest that from a broad number of points that are of interest to reach in a single day? What's the least number of stops that we need to make and in order to optimize the use of that single fleet vehicle? And now I add 10 more vehicles, and then 100 more vehicles, and then 100 more, or even 1,000. The idea that we can manage all those points and effectively pick routes, that's a very common application of AI today, which is certainly available today. Markets and products and services, we've talked a lot about portfolio management up above on the classification and prediction side. And when we talk about optimization, it's the optimization of the portfolio itself. How do we financially assess the capabilities of these power plants? What do they need to produce, and at what time should they be producing? And certainly when we add them in a couple million more power plants, how do our base load plants, how are they impacted? If we can push VARs at the edge of the system is a lot more efficient because we have many fewer losses to deal with. So this idea that distributed intelligence and artificial intelligence will help us both at the edge and centrally is an absolute truth. Let's jump to the next slide, please. So here we've really talked a little bit about this already, and I use this slide to reiterate the point that we're going to millions of power plants, and AI is going to be critical to integration and the optimization of these facilities. Here we have a customer facility which has been modeled with direct responsive systems. So they have inelastic systems, which means they can't respond. Are they direct control? Are they managed by an aggregator? Are they behavioral in nature? Is there some input, some piece of data, such as a price or an exposure to some market signal, commonly called transactive energy? Now, again, a buzzword in our industry, which is quickly becoming very, very popular. The idea that we can transact around these systems. How do we optimize those systems? Well, it's certainly going to be through the use of artificial intelligence. There's just too many decisions to make, and it's too complex of a system to treat it as just parts of a whole. We have to start to consider it as a whole, and AI will help do that. So now service provider operations and utility operations, how do we start to combine those two frameworks of operation together? A service provider doesn't have access to all the information that the utility will have information about. What level of information do we pass on, and how do we integrate across that communications boundary? So let's go ahead and jump to the next slide. So here we're going to dig into the value proposition in terms of AI for distributed energy resources. DER, the quickly gaining ground as a resource, and have already surpassed centralized generation investment. So with regulators expected to allow these resources to start to interact on their own in what we would call peer-to-peer marketplaces, although there's a question if they're really truly peer-to-peer. They're not peer-to-peer if we have a distribution service operator in between. I don't think that we'll actually have true peer-to-peer networks. There's always going to be a function for our DSO and our utilities, in my opinion. So here, in terms of the system value, we have AI controlling at the edge, fewer losses, higher returns, a greater ability to utilize our resources and optimize them. We can leverage these DER to support ancillary services and optimize revenue and control. And absolutely, in terms of situational awareness, how do we characterize a certain number of resources being on or off the system? If you're a distribution system operator and you have to manage reliability for your region of the grid, will you care if one EV disconnects and plugs in a different place? And the answer is no. But what if 1,000 of them do? And does that impact your planning? Does it impact your system reliability? And we all know that when cloud cover goes over a very large solar farm, we're gonna have voltage issues in the grid. Capacitor banks are going to have a function here, and how many other resources can be utilized in order to level out the responses. And this is all about the complex system. How many different systems are we watching, and how do we align them all together? And the answer is through the use of AI. So this operations perspective is about, what do we really think about the operations? How can we utilize AI for control? And here with DER, we're specific to their integration, and that we have to think of them as a system of systems. If you have one aggregator program and you have another program with some customers using EV and another legacy DR program using water heaters and another legacy DR program using some other direct control methodology for industrial equipment, and how do we combine these systems together? How do we manage the system as a whole? And so for AI applications here, we have prediction and control, which is a necessary component. We have the management of ancillary services, embedding those ancillary services into markets where that's applicable, and then the optimization, power flow and modeling of outages, and situational awareness modeling, scenario-driven analysis of in real time as events unfold in distribution and transmission operations. And then finally in market integration with the power marketing floor, requiring AI in order to investigate possible futures and be guided for load forecasting and market prediction. A really good example is wind in ERCOT in North America. How do we respond? What is our expectation of wind in the next hour? How do we prepare for it? So some of the types of AI in use today, we have artificial neural networks, which are certainly being used in power flow modeling, economic dispatch. Most power marketing programs utilize or are very near to utilizing artificial neural networks for their optimization and scenario modeling, and then absolutely in load forecasting. Agent-based simulation is being used more now. It's, again, been very common in social system research for many years, but is now just being drawn into our industry for program design, load, and revenue forecasting. We can absolutely apply agent-based simulation for behavioral analysis of customers under certain conditions. For example, how many EVs will be adopted in the next 5 years? Agent-based simulation is great for exploring that question. And then even economic dispatch, agent-based simulation for economic dispatch. ANN are used for security classifications. Fuzzy logic is used for security classifications as well. And then fuzzy logic has been used for controls for some time. And some ANN worth mentioning also for controls. Let's jump to the next slide. Transactive energy, we mentioned this earlier. Transactive energy, we're using economic or market-based constructs in order to manage supply and demand. Generally, we're thinking of transactive energy as something that is drawn out into our customer base. We're looking at customer resources and managing customer resources and their response to a market signal or a price signal or some other piece of information. the energy system value here, improving DER integration. Transactive energy systems have been proven in a couple of really large, in fact, the largest smart grid demonstration in the United States a few years ago, the Pacific Northwest Smart Grid demonstration demonstrated transactive energy. Here, the optimizing and leveraging customer involvement in order to help grid health, and then a platform for revenue with innovative services. Peer-to-peer management, for example. If you customers want to trade energy amongst themselves, there's a couple good examples of that happening today. Alliander in the Netherlands is running a transactive energy system, an auction, a demand, a bid in, where people's equipment are actually bidding in based on price exposure. And if the equipment doesn't bid in at the right price, then it doesn't get energy. So it's an excellent application and worthwhile looking into for anybody on the call. For the operations perspective, what should we be thinking about in terms of operations for transactive energy? We'll have exposure to distribution system operators, virtual power plant and aggregators, and then what we would call a transactive platform operator, the service provider who's actually running the transactive system or providing transactive type services. There's really three groups within the modern utility that must pay attention in the transactive energy system. And those are, we have power marketing, we have customer service, and we have distribution operations. And those three areas of operations must work together in order to manage DER, in order to make to get the benefits from these transactive systems. For AI applications, we can apply optimal portfolio and reduction of needs for capacity planning. How can we plan around these DER? AI is great for that. Power flow modeling and the balance of these intermittent resources. What can we expect in the future? Again, this is a classification and prediction problem. And then on the optimization side, the prosumer, someone who's able to both produce and consume energy at a site out in the network. These prosumers and energy service providers, how do we optimize response in markets? If they're not participating in the market themselves, then they need someone to participate on their behalf. You'll find that in many market situations where people won't have the capability to perform in the market themselves because it's a very complicated operation. And so, utilities have that capability today. And so they could be selling services to act on behalf of these prosumers. So types of AI in use today, or that have been tested for transactive energy, artificial neural networks have been used for load forecasting and for power flow modeling, and in fact for optimization of response inside the Pacific Northwest Smart Grid Demonstration Project. The particle swarm is used for power flow and for economic optimization. There's good examples out there. And then I want to mention something very interesting. So the idea that blockchain can be used for managing transactions. Blockchain is, this webinar is not about blockchain, but blockchain is very interesting because you can embed inside of the blockchain conditional, what we would call smart contracts. And so the ability to program this form of AI, and it's like a form of fuzzy logic where certain conditions are met, or conditions combine, then take this action. Those kinds of contracts can be written right into the blockchain. So expect to see lots about blockchain in the future when talking about transactive energy. All right, so let's jump to the final slide. If you would like to ask a question, then please go ahead and type in your question. I'm happy to field questions from the audience, and I just would also like to thank you so much for attending today. I hope it was informative, and also feel free to reach out to me personally. My email will be at the end of the call. Happy to start a conversation and see where it leads.
Yes. Thank you so much, Sean, for your presentation. It was definitely very informative and great. And we are accepting some questions. I'll give it a few seconds to go ahead and have some questions come in. But why don't I ask one just to get us started? Maybe someone will have another one, or they're thinking about one. You spoke very briefly about the role of the utility as we get closer to peer-to-peer networks. I know that we won't get to the point where it's direct peer-to-peer networks, but what do you foresee the function of the utility being as we get closer to that kind of a system?
Yeah, absolutely. That's a great question. Thank you. You know, the role of the utility is very solid in this future. I know that there's been some, just broad discussion in the industry. You know, what is the role of the utility in the future in this world where there are so many distributed energy resources? And truly, I see that role as being the same role as we have today. The utilities will be the network orchestrator of the electrical system. We're not going to have the capabilities to completely automate the grid. We'll always need system operators, and we're always going to need first responders. We have to manage the system in an intelligent way with operator intervention because you cannot predict everything. A very, very good example here is the tragedy that's occurring in the southern United States in Texas with the flooding. It's what we would call a black swan event, and it cannot be predicted. And so if it can't be predicted, then there's a probability that an event like this could happen, but you can't say when. And the benefit of being able to say that there's a 1% chance of this black swan event, or a quarter of a percent, or 100th of a percent of a chance of some event like this occurring, once in a lifetime. If you can't predict it, then our AI is likewise in the same situation that we are. It can be imagined by us, but it can't be predicted to a place and a time. And so the idea that as we move towards these peer-to-peer markets, the idea is to manage the operations as we continue to manage operations today, and very effectively, I might add. The real benefits in adding AI into the system is to take many of the more mundane tasks and assign those to an AI, and to do the exploration of the data and inform an operator of the potential to make a decision or to draw certain environmental conditions to the attention of an operator in order to elicit a response which is both effective and improving reliability and the robustness. And certainly in terms of resiliency, when we start to talk about microgrids, when does a microgrid, when does it occur? When do we disconnect from that transmission source and go off on our own? The idea that the grid can be a network of many, many microgrids, I think that's really the future that we're thinking of when we talk about DER. And when we talk about peer-to-peer networks, it's really about peers interacting within those potential microgrids, and then the management of their activity in a local way, in a more regional way, where we'll see the big impact from AI in improving operations. So I certainly see a place, not just a place, but the leading role in the management of the grid. Just as utilities continue to manage the grid today, they're always going to do so in the future. That's not going to go away. I think that there's a lot of new opportunities for utilities in creating new and innovative services in managing how that activity occurs peer-to-peer, where we'll have new revenue and the continuation of that line of business.
Okay. Great. Well, thank you so much. I appreciate the answer. Certainly good to know that we'll always kind of need the human element and also the element of the grid in its place to keep going into the future, and we'll still keep that industry alive, or that portion of the sector alive.
Absolutely.
All right. Well, I don't have any questions live from the audience for you for now, but I do want to thank you once again for your participation. And I do want to remind the audience that if you do have questions, you can reach out directly to Sean at Navigant Energy, Navigant Consulting, at sean.chandler@navigant.com. And remind you as well that you'll have access to the recording of this webinar within 24 hours. You can view that information on demand. And also for more information on our upcoming events or related webinars to this AI and Surge Energy webinar series, you can visit infocastinc.com. So thank you so much for participating, Sean, and thank you to the audience. Have a great day.
Thank you so much.
All right.